Share screen. Stop sharing. And then if I do okay, it's import. We finished all of this, right? We talked about the data hazard, right?
Yeah, we talked about the data hazard.
And we also mentioned about the forwarding, correct? Now I just tell me from the church. Okay. So if you guys remember, we talked about the 3 different types of hazards we have with the pipelining, right? We talked about what's the structure. We talked about data. And we have another one, it's called control. We're still processing the problems and, you know, how can you solve it for the 3 of them, right? We said in the structure, the best way to solve this problem is to do what? Is to have allocate more resources and replicating units. So every single stage, it can have 3 or 4 different units doing the same identical job. For instance, you know, in execution stage, and instead of having 1 ALU, we can have 3 ALUs, 4 ALUs, 5 ALUs, 5 cores basically. So if you, for instance, you know, you have a problem with accessibility of the memory, you can have 2 memories. You can have multi-input ports for the memory. So instead of accessing 1, you can access 2 of them at the same time with 2 different paths. And we define the structure hazard having based on the limited I/O and the memory accessibility, if you guys remember. Then we said there is another type of hazard we have, which is called data hazard. And this is actually suffering from the not, you know, the existence of the data, whether the data exists or not. Is this correct? So if the data exists, you can be able to process. But if the data does not exist at that time, so you are processing a wrong data, so that means you are just producing hazards. And the third inner line, which is a control, it's a kind of combination of what we have in the structure and data, but in the control level, which is even worse to debug and reverse engineer. We mentioned to fix the problem of the data hazard is to have 2 different types of solutions, one in the software level and one in the hardware level. The software level, we call it what? A reordering or rescheduling the data by adding bubbles or idle statements in the middle of the instruction that's suffering data hazard, or putting another instruction, locating another instructions between of them doesn't have any dependencies with the instruction we are processing. The second in the row for solving such a kind of problem, basically we call it what? Forwarding, which is a hardware solution. By adding a multiplexers with feedback from the stage to the other, so every single stage will be connected as we are looking for. 1 second, because my screen went off. So forwarding is basically, it's a one way to fix the data hazard. So this type of questions can come to you in the exam as a true or false or multiple choices, right? So one of the questions, we have 4 types of the data hazard. We have 4 types of hazards that pipeline is suffering: data, structure, control, and memory hazard. Is this statement correct?
Yes.
Nope.
Okay, well, I already got it wrong.
Because what I said data, control, data control, structure, and memory. There is nothing called memory. They just have 3, right? Data, structure, and what?
Control.
And control, yes. Okay. So the most obvious cases for the data hazard is the ALU accessibility, not the IO limitation. Is this statement correct? For the structure hazard.
Can you repeat the question?
Okay, so for the structure hazard, the most reasonable problem for causing the structure hazard is the ALU accessibility, not the IO accessibility. Is this a true statement or a wrong statement?
Can you give an example for that?
I will tell you, it's not, without example, ALU, it can cause the structure hazard, but the most famous problem is the limitation of the IO. So because we have single input memory, single output memory, that's actually causing the structure hazard. This is one of the most famous problems. Of course, ALU can happen, but actually caused by the IO problems. The best way to solve the data hazard is to reordering the program or reschedule the problem, the program you are running to solve the data hazard. Is this a correct statement or wrong statement?
I mean, you could do both.
Yeah, but it's a correct statement. It's a statement that's correct, If I have a data hazard, it's better for me as a software engineer to rewrite my code somehow to avoid the data hazard, right?
Yeah.
Because the problem with the hardware solution, if the processor I'm using is ASIC based, you cannot change. Do you agree? But if the processor is a soft-core processor laid on the FPGA, yes, I can change. Make sense?
Yep.
So anyway, this type of questions we can have, okay? So there is a story. When I say it's a solution, it doesn't need to be, it's an ultimate solution. Everything in this life relative. What does it mean? So actually the forwarding or the restructured or rescheduling, the reordering or scheduling the instructions in the code, it's solving some problems, but not all the problems caused by the data hazard. Because if, for instance, if I have an instructions loading word and storing word, followed by another instruction, which is basically R type can be added or subtracted, there is no way for me to solve this problem, no matter I actually order or not. Because the accessibility of the structure level happened by the load word will be reflected on the data hazard happened by the R type. So you need to know the limitation of your solution. There is no ultimate solution, okay? So data hazard here in this code, I am actually loading word, and that word coming from the offset 0 and the base written in R2, and the data pointed coming out of the memory will be loaded in R1. But I need multiple cycles for this instruction to be executed in the pipeline, because I have 5 stages, if you remember, right? But I cannot immediately go and say subtract directly R1 to R5. I have to stall. I have to stop here completely 5 or 4 cycles. It depends on how many stages I'm in, until the data will be what will be drained out and will be ready to be placed in R1. Then I can be able to use it. So forwarding as a solution is not an ultimate solution. Still, I have to use the tricks in the software to solve the problem.
Dr. Lee?
Yes.
Why did you mention that it would take 4 or so cycles? Is it because there's 4 different instructions?
I'm just going to example, because
okay.
if you remember, there is instruction fetch, there is instruction decode, there is an instruction execution of the instruction, there is memory accessibility, there is a write back, right?
Right.
So where exactly I am and how many cycles until I will be saved, that will be coming. Maybe it can be 4 cycles, 3 cycles, 2 cycles, right?
Right.
So that's basically the whole entire idea. So forwarding, it's a solution, but it's not an ultimate solution, because it's not solving to me the needs I need, because it's still, even though that I'm forwarding from backward from a stage to the others, there is the points I have to wait for 1 cycle or 2 until I will receive the right data, right? So forwarding, it's a solution, but it's not ultimate solution, while the best solution ever you can have is to restructure or scheduling the instructions you have in a software. Sounds good?
Sounds good.
And that's actually the slides in front of us is showing us the problem and how can you avoid it, especially if I am associating something related to the memory, like loading word and storing word, and in the middle I have a bunch of R type I'm trying to execute or processing the data coming from the memory. Okay, that's showing you how it works in a very efficient way. Anyway, back to the point. Stalling or stopping the processes until I drain, as we start defining the pipelining, when we said, we can pause or drain the data, that show that some of the situations unfortunately, I have to drain the whole entire pipeline until I get the right data, then I resume, right? And that's actually defined to me as what stalling as one of the rescheduling solutions. One of the possible things that I can bring to you in the exam is to give you a code written in C and ask you to write the code with ability for avoiding the pipelining. You know exactly how many instructions you will have. Every single instruction based on R format or load word and store word and control, how many nanoseconds will take, how many cycles will take. And that was very good practice in the midterm number 2 to have such a kind of table, and you guys fill the number of nanoseconds it's gonna take per instructions. So that's a very good way for you to practice before you can start writing code and avoiding a kind of data hazards can happen. So the code in front of us here, in the left side, it's very clear that there is a hazard happening. And the solution for me is actually to reschedule. And luckily, when I rescheduled, the total number of cycles, the code we're taking, it was 13 in the beginning, and now I have 11 cycles. So that means I made an optimization while I'm rescheduling, and you can see that. So for instance here, I'm loading the second word, there is no problem because, end of the day, I'm using the same type of instructions. But then, I'm here dedicated to process data in T2, whether T2 is not exist. So in that case, I have to do all of the load word in the beginning. So I will be sure that there is a shield happening here, which is actually making a kind of artificial bubbles or stalling until I will be sure that T2s exist. And from there, I can even wait one more time. So I can T4 will be exist and I can process the data. So the type of questions can come in exam, write the code that will be associated to the C code and avoid any type of hazards or data hazards.
Professor?
Yes.
This is a little bit off topic, but is this the reason why it's good practice to put all the initializations at the top of the code?
Yeah, that can be one of the strategies, yes.
Okay.
So, you don't need to, because think about it, right? If you are constrained by the amount of time you will be taken to finish a certain task, especially if you're working in a company, right? You have to go with like a general rule, as you said, put the initialization in the top, be sure everything is perfectly sorted. Also, while you're making branches, be sure that you are calculating every single level of the branches before you will make a comparison between of them in enough time, then, other will not happen. You know what I mean? So this is like a general rules. Yes, you're right. Okay. Any questions so far? Hello?
No questions?
So far, so good. Super. And now we're going to go into the most important problem pipeline is actually giving us, which is called control hazard. So control hazard, as you can think, what type of control we are doing in the assembly? We are just jumping for jumping, right? Or we are having, if this happened, jump to this branch. If not, jump to that branch. Is there anything else control-wise we have? So we have jumping with what condition? Jumping without condition. So what will be the problem ever we can face caused by the pipeline? If the two registers, for instance, in the condition process are not connected correct or not producing to me the right output because of what? Data hazard. So let's say that, if the data in R1 equal the data in R2, increment the PC counter 15 times. But the data in R1 didn't arrive at the time it should be. So that means, this condition will be completely what? Wrong. So that means, I'm going to be incrementing something completely what? Wrong. So that means the whole entire branch will be wrong. The whole entire program will be producing output wrong. So way to solve this problem is to eliminate branching. As much as you can avoid branching, right? Or process the data as Mark mentioned, initially in the top, be sure there is enough time, make all of this initialization in the fair top, and after that, do what? Do the processes later on, so you'll be sure the data is already correct. Somebody is still in the, Did I allow him? I don't know, I think so. Okay, sounds good. Anyway, so one of the solutions for the branching is to actually also stop. Have you noticed it's just repeated words, right? The whole concept is very easy. Data came early, we should be waited a little bit. Waited even though that I'm gonna make some artificial stalling, or I'll completely like idle the whole entire thing until the data will be drained. That's it. And that's basically what we have in front of us here. I added here extra line doing nothing, just to be sure the data coming from the branch equal is already correct and happened. And based on that, I will be jumping, and I'm 100% sure that I'm jumping in a correct way. So one of the most famous questions, what type of tech or techniques I have to follow to solve the control hazards? First, I should have like a snapshot of my what? PC counter, right? Because if I would like to reverse back and figure out what was my problem, at least I have the copy of the snapshot of the previous what? Instruction. That's correct. That's why we have something in the computer. It's called watchdog. Did you guys heard about it?
Yeah.
So the watchdog is recording the trip of the instructions while you are running. By enough time that, if you have some problems, you can return it back and pick up this snapshot, and you will investigate and see what is the problem, and you continue and resume. Second possible way, completely avoid branching. Third way, it's not written here, but later on we're gonna see it in the next slide, is actually to do what? Branching prediction. So we will make assumption. And based on this assumption, we're gonna go through the tracks of the branches I have, and then I will be able to fix the problem I am facing. So as I mentioned to you, what is the most critical problem ever control hazards is depending on is the data. Is my data is not correct, which is data hazard, then control can happen. That's why I stated here in front of you. Control hazard costs more than data hazard, and data hazard actually is causing the control hazard. Sounds good? If I want to fix the problem, I can fix it by determining the branches early. So if I go and if R1 greater than R2, but here I calculated R1 is basically R2 plus R3, but then, I'm using pipeline. This is not ready. So that means, this if statement is wrong, I'm branching wrong. So I have to do what? Branch condition early. And also, as I told you, using the watchdog for snapshot the PC counter. So here you calculate the PC counter, save it somewhere else. I will check, or you can make both later, and that will be fixing the problem. Techniques to avoid any type of installing while I'm doing control hazard avoiding. I have to follow some steps because, if I go ahead, for instance, and I do this right by adding extra bubble, it's a solution, but it's not solving the whole problem. It's basically causing me to be slower, right? And the whole entire trick, the whole entire business in computer architecture, be fast, use less resource, and use less power. If you can fit into the 3 different categories, you are computer architect in a grade number 1. So to eliminate the stalls as a solution to avoid the control hazards, you have to follow these techniques. And that's a very, very nice candidate questions in the final. Like, first of all, I eliminate branching, as I said. Second, I do prediction of my branches and completely take a snapshot of the branch so I can reverse back and see what is the problem. The third is actually moving the comparison early as doing the whole initialization as Mark was talking about, or you delay portion of the slots, not the whole entire instruction. So those 4 techniques are the best to avoid stalling while you are fixing the control hazard. Is it clear so far, guys?
Can you explain that again? I'm sorry.
Sure. So if you remember in the control hazard, if I don't know the branch is correct, then the whole entire thing would be wrong. Do you agree?
Yes.
So as a coder or the developer, right? If I would like to stop using the stalls if I have any hazard, in the beginning, I need to eliminate branches. Do you agree?
Yeah, I agree.
This is the one. The second, if I cannot eliminate branches, and I have to use branches, what I need to do? I have to move forward the testing above. That means, R1 versus R2. I do this early, and I see that R1 and R2 are exist. So that means I'm 100% sure R1 and R2 are exist. Then I will be able to do the branching. That's called move comparison testing to the early stage. Sounds good?
That sounds good.
The other is to make delay in not the whole entire instruction to be delayed, pieces of it, right? Like, do you remember when I made the bubble? Do you remember when
the little bubbles?
One, huh?
The bubbles and the delay. Yeah.
Yes.
Mm-hmm.
Yes. The last one, which is the new one, branch prediction. You're going to use a statistical modeling to predict while you are reversing back, so you will be able to debug.
I see. Okay.
So, you say, oh, I have to go line 150. But then, I went to line 150. I do some tests. Oh, it's wrong. So I have to know that, what was the branch before so I can jump back, right?
Right.
That's branch prediction.
I see. Thank you.
You are most welcome. Anyway, that's the only thing that we finished with the chapter 4. The rest of this slide is just repeating and repeating and repeating all of the information we shared together on the chapter 4. So if you guys remember, what was chapter 4 about? the implementation style of the processor. That means I'm looking into the hardware communication between the parts of the processor on the chip. We started by the style of implementation. We said there is something called single cycle implementation, there is multi-cycle implementation, and there is a pipeline implementation. We moved to the single cycle implementation. We found it is really naive implementation and straightforward. We came into the conclusion that, you know, single cycle implementation is not really efficient, right? Because, you know, if we are RISC architecture, that means every single instruction is actually using one cycle for implementation. And if we start looking into all different format of instruction we have, we'll find out that, you know, which one is most consuming time. The one is working with the memory, which is the load word. All the 5 stages will be what? Running. So that means the critical path will be very long. That means maximum frequency will go down. We start saying we need another solution. We said there is a multi-cycle implementation, or there is what? Pipeline. I didn't go too much in multi-cycle, but you know, it's understandable. What is multi-cycle from your point of view is, instead of having in every single stage one element to do the job, you're gonna have multi-elements. So instead of have single core, in our case, what is the core in the computation elements we have? ALU, right? Arithmetic and logic unit. So if this arithmetic and logic unit is repeated many times, then I don't have any problem. Instruction number 1 will go, it will go to the first ALU, while the instruction number 2 will go to the second ALU, and the third ALU, and the fourth ALU, and so on, right? What is the drawback of the multi-cycle from your point of view? The drawback of the multi-cycle implementation, many. One, I'm using more resources. You guys agree? Because I'm building more cores. So that means how, you know, the power I'm gonna be used, it will be what? A lot. You guys agree?
Yeah.
The second way of actually using multi-cycle implementation is to look into the longest path and chop it using sequential circuit. So instead of running in, instead of running in one big cycle with like 50 megahertz, no. Make the whole line running in 5 cycles and running 400 megahertz. But still is acting as a single cycle because I cannot take the second instruction while I'm executing the first instruction and so on. But at least I push the maximum frequency a little bit higher. That makes sense?
Yeah, that makes sense.
Okay, now we came and say why we need to add too much resources. Let's go into the pipeline. So we went in the pipeline. We found the pipeline. As you know, MIPS is a RISC architecture example. We have 5 stages. Instruction fetch, instruction decode, instruction execution, instruction, you know, memory accessibility stage, and the write back, whether it's gonna be to the memory or to the register space, as we cannot process data in the memory directly, we have to host it temporarily in the register space, correct?
Yeah, that's correct.
Then while we are moving and developing the process, we figure out, you know, every single instruction, it has its own what style. Some of the stages is turning on, some stages is not turning on, and so on. And also in the early stage of the chapter, do you remember all of this blue thing that I was sharing with you? R type, some of the stages will be on. I type, some of the stages will be on, and the rest will be off. J type, some of the instructions will be activating parts and the other will not be activated. Then we found pipeline is really cool. Pipeline in a line instructions is not fixing a problem. End of the day, I have to pass 5 stages. But we found out if I'm running big portion of data and partitioning this data on the elements or units I am sharing, that will fix the throughput. Okay. Then we came into the very nice conclusion. And you know, pipeline is great, but the pipeline have to follow the slowest footsteps or the slowest step out of the 5 stages I have as a MIPS architecture. As a MIPS processor RISC architecture example. So the slowest one is what we're gonna follow. But then, because I'm following the slowest, some of them actually faster than that, we have to use what bubbles to compensate these errors, right? And we made the example of the washing machine and drying and so on. Then we came into a very nice conclusion. Nothing for free. There is no lunch for free. So what does it mean? It means there is actually problems we're gonna face using pipeline while I'm streaming. And if you guys remember from the chapter 2, I was telling you that, you know, what MIPS mean? MIPS was without interlock. Do you remember the interlock and without interlock? You remember this discussion?
Yeah, I remember it. I just need to review a little.
Yes, so when I say with interlock, that means every single stage, when it go to the second stage, they have a kind of protocol for acknowledging and requesting data, right? While streaming without interlock, that means, you know, every single stage is just dumping data to the next one, no matter if the second one is what, free in a process or not. So if I'm streaming and I'm pipelining as an early stage of MIPS, what will happen? Hazards. What type of hazards? If you are memory accessibility limitations, or you are limited of number of resources used per stage, you are suffering from a structure hazard. How to solve it? Replicate number of structures, number of elements per stage, or you will try to organize it by what? Stalling. Then there is a different type of hazard called data hazard. This data hazard is actually caused by what? The wrong existence of the data per time. So the time slot, the data wasn't existent in the right place. Big problem. Solving this problem, software level is reordering or rescheduling or stalling. Hardware level, forwarding by using multiplexer with feedback. Forwarding is not the ultimate solution. Why? Kind of like, you know, combination between the I type and R type, as I'm loading word and storing word forward by R format, forwarding still will not solve this problem. So software level solution is a kind of more efficient than the hardware solution, but of course, hardware solution is solving some other problems. Then we came into the control hazard, which is caused by the structure, data, and also missing branches and stuff like that. And we found out that, you know, if we figure out a way to eliminate the branching, or, you know, calculate the elements gonna be associated by the comparison that, you know, for the condition purposes early enough, then you will go ahead and, you know, execute the branching. That would be a very good solution for both of them. Then we said one of the way to do it is the stalling, right? But, you know, if you would like to avoid the stalling in the control, there is 4 ways to do that: by delay slots, or, you know, eliminating the branches from the beginning, or early calculation, or the branch prediction, as I mentioned to you. And we close the chapter. Does make any sense?
Yeah, it makes sense. I just got to review a little. Yeah.
It's an easy peasy lemon squeezy chapter, by the way. The only thing you understand R and IJ type from chapter 2. That's it. Here, I'm just sharing you the same story. As you know, as we are engineer, we have infinite solution for any single problem we face. Any normal human in the earth is not engineer. He can barely find a solution for a certain problem. For us, we have to find infinity solution for the problem. So whatever, you know, I use as a way to convey the message to you about, you know, the chapter, I wrote it in a different way in the slides, and I give it to you as another way. So if you don't understand my way in number 1, you can understand my way number 2, which is leading you to the same answer. So that's why, you know, I put here in front of you the hazard with control and, you know, all of these tricks, as you can see. Okay. It's just like, you know, repeated it information, but in a different way. Sounds good?
Sounds good.
Now, let's get summary, which I already said it, but, you know, it's written, okay? What's make it easy? All instructions are the same length, just a few instructions format. Memory operands appear only in the load and stores. What's make it very hard in the pipelining? Structure hazard, control hazard, and data hazard, right? Also, pipelining is a fundamental concept. We already use it in the washer and dryer. You know what I mean? We can use it in any way that, you know, we would like to use. multiple steps using distinct resources, utilizing the capability of the database pipelining. So you have to start in next instructions while you are working in the current instructions. And then, you know exactly that, while you are doing the work, sometimes you need to drain or sometimes you need to pause. It depends on what is the situation. And of course, this way is kind of helping you to reduce the effect of hazardness. Is it pipeline is easy? The basic idea is very easy, but everybody know from whatever we learn in our life, the devil is in the details. Because once we start putting our hand, running different scenarios of instructions following each other, we found there is a bunch of what? Hazards. Okay? Pipelining is independent of technology. Do you agree? Because end of the day, the transistor is smaller, faster, whatever, still, the number of stages is the one is actually what affecting on me. That makes sense? Hennessy and Patterson in their books, normally they make this pitfalls, whatever, slide, which is basically telling you poor instruction set architecture, which is standing for ISA design, can make pipeline harder. Is this correct statement? That's basically what they're talking about. So example for this is basically something that's called IX and VX, and those are very complex instructions we haven't talked about as we just in a 80-80 steps of learning architecture. That's why we took risk. Okay. Complex addressing modes can actually causing a bigger problem. Yes. It's a problem and it's not problem. So you can consider it wrong and yes. So that's why, he made the pitfall thing. Delay branching is the best way for solving the problem of the hazard. Of course, sometimes, not all the time. Here, bunch of concluding remarks. You can figure it out based on our discussions. And the reference of the whole entire work and the slides I shared with you about chapter 4 from Hennessy and Patterson book, and the official website for MIPS architecture people, and the Stanford team who built the VLSI part of the MIPS processors, and Naga notes I used 4 or 5 years ago, I don't know, when I started working at Calpoli. If you have any questions, let me know. I haven't seen anything. So, let's, we talk first about this slides on chapter 4 and we talk about the other issues. Okay. Sounds good? Any question regarding the material of chapter 4? Okay, so now we just have one chapter left, which is chapter what? Chapter 5, which is gonna be memory architecture. And we're gonna start on this on Wednesday. When is the first draft due?
26th.
Huh?
The 26th.
26th, soon, okay. So do your best on bringing this to, on that day so we can discuss it in detail.
Professor?
Yes, sir.
You said you wanted the IEEE format, right?
IEEE or ACM, whatever you feel more comfortable with.
Okay, gotcha. Thanks.
If you are happy with this, that's fine. If you're happy with the other one, that's fine also. Okay, look. Now for the exam, I noticed, I think a couple of you guys missed the time slot from 8 o'clock to the midnight, right? I'm gonna pass it this time, but please, in the final, that will be prohibited. That makes sense to everybody?
Yes, sir.
Yeah.
I can repeat that. Some of the cases sent an email regarding the problem with submissions on time. And if you guys remember, normally in a normal case, any exam at Calpoli here, it take 1 hour, 15 minutes, right? And finals normally take 2 hours, right? But you know, because I'm trying to make it easy for everybody, I decided to make it from 8 o'clock in the morning to midnight, so you guys will not take, you know, will not be too much stress on you. Internet went off, you know, somebody got sick, something happened, you know. So you know, you will take your time. But this is a privilege. I don't want you guys to misusing it. That's basically the whole idea. Okay. So some of the cases happened. Okay, I understand, and I will help. But you know, from next time in the final, be sure to submit your work on the time, from 8 o'clock in the morning, midnight, 11:59. Is it sounds good for everybody?
Yes, sir.
Yes.
Okay. There is no exception. There is no exception. I'm sorry about that, but there is no exception. Sounds good? For this, for now, at least for you know, for this time, I'm gonna pass it. But final, no. Okay. Thanks so much for your time and effort. And by the way, I'm really proud of all of you. And you know, you guys are doing a really good job. And it was my pleasure actually to be teaching you this course this semester. I hope to see you guys hopefully physically on the coming semester. Okay. So God bless all of you. Please look at the Slack again, as I posted something interesting for the robotics thing for NASA. If you like to join my team, that will be great. And I promise we're gonna do a lot of work. Okay. Thank you guys. God bless you.
Thank you, Professor.
Thank you, Professor.
Thank you.
Thank you. Take care.
Thank you, Professor.